Thank you, Dr. Sargent, for introducing me in such a nice way as Tarleton's best biologist. Oh, where's the voice? Sorry. Tiger biologist. Thank you for sticking in this really cold room. I'm suffering here. I wonder how you guys are here. It's really tough. But that was very enjoyable to hear two talks before. And when both of you guys were talking about goats, cows, and especially the lame cows, I was thinking about how those lame cows might impact intragrill interaction between leopards and tigers, because healthy livestock might have different impact, while lame, they're not very healthy, right? Yeah. So they might have different impact. So whole thing, like surrounds, as Dr. Schroeder mentioned about carnivore thing. I think I talk so much about carnivores. If evolution would happen in one lifetime, I would develop a canine. So yeah, a lot of carnivores. So we'll talk about tiger and leopard cooccurrence today. So basically, carnivore has been revered as the top tier predator which helps maintain ecosystem, right? So the carnivore conservation has been central in conservation biology from ecological standpoint and from social political standpoint as well. So when there are a suite of multiple predators, as I have mentioned here, well, my talk is basically on tigers and leopards, then how these two species co-occur has been a central question about how intragrill interaction takes place. So, and why we are so much concerned about intragrill interaction is that, as we're aware, that intragrill interaction can range from interference competition to all the way to intragrill predation. So there are several theories that have been put forward about how these interaction shape co-occurrence between large carnivores, especially the sympatric carnivores. So there is this study from Dr. Sargent-Sticker from 1970s where there were a lot of forest areas and a lot of prey base, a lot of large prey base basically, and he found out that the amount of large prey base and also larger proportion of smaller prey base basically help co-occurrence between tigers, which is almost like 4 times bigger than leopards. So leopards have prey, tigers have their own large prey base, and that's how they would co-occur. So that would dampen intragrill interaction, be it interference competition or intragrill predation. Now, as the predator areas are shrinking due to habitat loss and several other reasons, now what we see is how in smaller predator areas do these species co-occur now, because the habitat is shrinking and prey base is depleting. So how do they co-occur still? Because with time, the dynamics of the population changes as with the prey and consecutive impact to predator as well. So there is another study done by Orden and colleagues on how do tigers displace leopards, if so, how. So they tried to investigate this based on scat analysis and territory analysis, and they came up with the idea that it's the prey base. Basically, as you have more prey base, then it is easier for tiger and leopard to segregate their habitat, and that's how they can co-occur in same area or in same habitat. Now, well, their data and their hypothesis was proven, were supported basically, and it sounds like true, but necessarily that does not happen in all carnivore model system, because not necessarily the increasing prey base or density of prey will facilitate that. In some instances, like if you have an example of African wild dogs and lions, what happened here was as prey base increased, the interference competition between lions and wild dogs increased even more, and that triggered wild dog population to go down. So that means, as we talk, we mention as enrichment paradigm. So you can have counterintuitive impact of increasing prey base to the subordinate predator when there is a top predator which has impact on the subordinate predator, which can also basically, as we saw in the previous slide, that can also result in integral predation. So to look at this now, and after realizing that these protected areas are constantly shrinking and still species are co-occurring, so what could be another mechanisms beyond these hypotheses what people have proposed earlier? So we thought that there should be some fine scale habitat use mechanism, or there should be some fine scale habitat factors that might impact occurrence of tigers and leopards. So first, we conducted this study on fine scale habitat association of tigers in Chilwan National Park in Nepal. So this study gave us confidence that though carnivores are large ranging species, their territory and home range are fairly large, but still there could be other mechanisms operating at a fine scale that could restrict the activity centers of tigers and leopards. So we thought about, well, if that's the case for tiger, then that could be for leopard as well. So we expanded this research in an occupancy modeling context to work on how integral interaction, how co-occurrence of tigers and leopards are possible in this habitat. So there are a couple of motivations, like why we chose a couple of covariates to see why we used human and livestock as a covariates for studying integral interaction. The first thing is the human-tiger conflict. Human-tiger conflict has been a pressing problem where we find a lot of human casualty as well, not only just livestock loss or livestock casualty. So as tigers number increased, as a mandate that we got from Tiger Summit in St. Petersburg in Russia, so the tigers number has increased, and now as you can see, the number of human killed per year has also increased a lot. So there has to be some sort of impact that human does on occurrence of tiger as well, right? And there are also a lot of livestock, because this area I'm talking about is basically agriculture-based area. So there are tons of livestock which are not still fed, but people just leave them, what do you call that in livestock terms, I don't know, kind of stray in the forest. So they venture in the forest, okay, venture in the national parks, where they can be easily taken by tigers or leopards or any other carnivores. So there are these situations. So apart from other hypotheses I talked earlier, these disturbance factor, what we call as disturbance, might mediate the interaction that tigers and leopards might have. So we try to investigate that, and you might be thinking, some of you have done a lot of research on using multiple covariates and a lot of data. You might be thinking, why only a couple covariates to define that, right? And we'll see in a second why I have done that. So my research question basically is fairly simple. It's just what effects do prey, livestock, and human abundance have on the occurrence of tigers and leopards? So that's fairly simple. So I kind of combined different hypotheses, different set of a priori hypotheses to see how, well, basically I have combined different a priori hypotheses to come up with the idea that tiger occupancy is negatively influenced by human and livestock abundance, which is fairly obvious, but positively influenced by wild prey, that's also fairly obvious, thereby facilitating leopard occupancy in sites with high human and livestock disturbance and low wild prey abundance. So conventionally, what we have been thinking is as prey increases, that supports leopards and tigers both, right? So, and as I already mentioned earlier, the competition theory, the traditional competition theory of basically Lotka Volterra, that may not necessarily hold true, right? So we try to see if low wild prey abundance might support leopard occupancy, thereby facilitating co-occurrence of both species at a fine scale. So there are a couple of things here at a fine scale and integral interaction as a function of human and livestock disturbance and prey. So we found those three factors could be most important in shaping interaction between carnivores. Okay, so just give a glimpse of how we do this occupancy survey. So we used remote camera trapping techniques, and you can see here that's just me. I'm not always like this, okay? Most of the time I live my life like that. So we put cameras, basically what we did was we put cameras in 361 locations. And we did camera trapping for 17 to 21 days, day and night, for having repetitive data on capture and recapture. And we use this data not only for tigers and leopards, but also for prey species. So conventionally, prey density estimation is basically done using distance sampling, which is more labor intensive, and the data that we get from camera trapping on prey has not been effectively used, and it's only has been used for tigers and leopards occupancy modeling or spatial capture marker capture analysis. But we try to use this data generated by camera trapping also to estimate abundance of prey, and we use that prey abundance as a covariate in our interaction model. So basically our data looks like this, if where 1 is if your tiger or leopard was present, and 2 whether and 0 is when that was absent. So these are the days we consider as sampling occasions. These are the grids that we sampled. Remember that this is only for one species. Now we're talking about 2 different species, and this can be very unwieldy and very big. Okay, and we'll see. I'll just show that, and I'll not even talk about it because that's going to be, I mean, half of this room will be empty if I start talking about that. I don't want to do that. Well, a little bit about how we use that. This data basically, as we use 1 and 0s for tigers and leopards as a proxy for occurrence or non-occurrence per leopards, for prey, what we did was we counted independent photographs of prey and tried to use some mixer models to estimate, I wouldn't say accurate, but robust, to come up with a robust estimate of the prey species. So for that, basically what we have is kind of data analogous to count data. So for this count data, basically we model that in 2 different steps, which is called basically a hierarchical model. So, and don't worry about all these things. What we have is different numbers at different grids, okay, different grids for different prey species like cheetah and chamber deer that I have considered here. And basically that count comes from 2 different processes. One is the observation process, what you see, how many numbers you see as Yij, which is basically binomially distributed with the state variable n, which is basically the abundance what you have at this point or around this point. We can consider around this grid. Okay, so here this Yij is the observation process, is the count that you got, and Ni is the abundance, which is a function of mean abundance of this site, and which can be distributed as per your distribution choice. And you can use Poisson distribution, which is basically used for count data, and also, but this data can be very heavily over dispersed, so you might want to choose other distributions as zero inflated Poisson or negative binomial or anything like that. So this is basically a 2-step process where you can estimate your abundance estimate using your detection probability as well, because this Yij is not just that raw count. It also depends on the detection probability P, not just Ni. So now what we can do here, and here's come why we use less covariates than people might want to use, is because now what you got to do is you got to model the impact of all the covariates on your detection probability as well, which can be a logit function of any covariates. Here we have used, let's say, 3. So you can have the impact of these on the detection probability of any site I at survey occasion j. So now, and that detection model now fits into this abundance model, where again all of those 3 covariates can contribute here. So now with this model can get really complex, and as you increase your covariate, the impact can get blurred, and then the interpretation can be really difficult, and it will be hard to segregate what impact it has. And remember that we are not just talking about one species here, we're talking about the interaction between 2. So that can be even more tough to interpret biologically, though we might get p less than 0.005, whatever is that, I don't care. But you might get that. You might say, well, that's significant, I got it. I have no idea what does that mean. But biologically, that can be really tough to interpret. Okay. So these are the different pair-evidence covariates that we used. So one was the water distance, elevation, and NDVI. So we thought NDVI, which is basically the normalized difference vegetation index, which is a measure of vegetation greenness, would be factor what our prey population depend on, and water obviously is really important factor, and the elevation. So now what we got to this model is we got fairly good estimate of trend of prey density based on different covariates. Now, and we got the similar results for different other prey species as well. I'm not reporting all of those because we don't have time. So what this the benefit of this model for estimating prey is, first, we did not rely on the data, just observation data, and we incorporated detection probability that basically enhanced the quality and also we incorporated different covariate impact. So that basically gives a plausible trend of animal abundance. Okay. Now we use that abundance of cheetah, which is like spotted deer axis. You guys must have seen axis invasive in Texas, I believe. Well, it is, right? So axis, which is the main prey, and somber, which is also main prey. This somber is a large prey, service unicolor, and axis is considered as medium-sized prey. And these prey basically overlap in diet of tigers and leopards. So we used these 2 prey species as surrogate for prey abundance, and we used independent capture of human photographs and independent photographic capture of livestock, regardless of lame or not lame. Okay. So now let's look at our occupancy survey data for carnivores. So I just try to give a snapshot of how tigers and leopards are located in that landscape. So this is our study area where you see, this is not abundance, okay, I'm sorry for that. So this is basically the number of independent captures of tigers in different grids, and these are basically 30-meter grids. And these for independent captures for leopards. And when you look at where both of these species were located, now when we see these grids where both tigers and leopards are located, that does not necessarily mean that they co-occur. So that's an important point to understand, because we have not included any other factors that might have impacted these. So now what we are trying to do is we are trying to use our hypothesized covariates to see whether those factors impact co-occurrence pattern. I'm not very happy to show this, but the problem is that unless I show this, I can't really tell what's going on. So basically what we did from our occupancy sample, I showed here in a beautiful picture, but just overlaying those two does not really, as I mentioned, overlaying those two does not really tell us about the co-occurrence. So we got to look at how the detection and non-detection of tiger or leopard was in particular grid or in particular camera sites. So what we do, we create this detection history for tigers, this for tigers and this for leopards. That's just an example, okay? And that now this detection histories again, as we did in our abundance model as well. For this model, now your detection, this is basically a latent state of occurrence, which is basically a Bernoulli process, right? Whether you detect it or whether you not detect it, right here. And so this is a Bernoulli process of occupancy. And when you look at this observation process of Yij, whether you found that species or not, again, it's the Bernoulli process of this state variable with the probability of detection of P. So now we're going to include these factors to contribute to our model. Now again, just to add to that, for the occupancy, again, what we can do is we can introduce whatever variables that we choose as our covariate that might predict their occupancy. Now remember that we're just talking about occupancy and we're talking about one species here again. So now we're going to work on this for two different species at the same time. So now how that looks like is if you look at this two species occupancy model framework. So let's say you at n sites your A, let's say is tiger. If tiger is absent, that means absent means neither tiger nor leopard was present, or B was present, which is leopard was present but tiger was absent. So this could be one situation, and this situation will lead to these two different situations. Now here, if tiger was present, thank you, sir. Then what happens is if only tiger was present or both were present, right? So now we have this situation that we have different situation of occupancy where both can be present or only one is present and the other is absent. Either tiger is present or leopard, or the tiger is present and leopard was absent, or both of them were present. So now we've got to estimate for all of these. So these are the parameter estimates that we use for two species occupancy model. Forget about that. And these are the parameters that we use. So these are the parameters that we use for two species occupancy model where, please don't swear at me. Because, and I will not talk about all of these, but when you model these parameters, then what you can tell is, in a simplistic term, is what would be the impact of livestock on occupancy of leopards when tiger was present, or what would be the impact of livestock on occupancy of tigers when leopard was absent, and so forth. Okay, so there are several situations of either detecting it or not detecting it, or either site being occupied or not being occupied. Okay, so we are working on that, and probably when I submitted this to my advisor, this was his situation. Half bottle of whiskey was already gone. So now after this, when we estimate all these parameters that we saw earlier, now we can calculate species interaction factor that will tell us whether the species does co-occur or not, whether they avoid each other or whether they're randomly distributed and they don't care, whether tiger doesn't care whether there is leopard or not, and leopard doesn't care whether there is tiger or not, based on the covariates that we have used here. So this is the outcome of the model that we got. So we're not going to detail about how it works. So we worked on a program called program presence, which calculates these values and we estimates all the parameters. So based on our top model, what we got, our results was our livestock was negatively associated with detectability of tigers. So basically, when livestock increased, detectability of tigers decreased. That means there could be two reasons for that. The first thing, as we saw in our different hierarchical process, there could be two ways. Either they were not detected, they didn't want to come out when they were leopards, or it could be the function of their occupancy as well. If the occupancy is already low where there are livestock, then the detectability could be low as well. So there are several factors. And the livestock had a positive influence on detectability of leopards. That means if leopards are there, if livestock is there, then leopards tend to come out. So that also explains the conflict between leopards and livestock, which is normally attributed to tigers, and tigers are killed in retaliation. Because people say, well, the human-tiger conflict and lots of livestock are killed. Well, our model tells us that that livestock depredation may not be because of tigers. Potentially that's because of leopards. But if livestock is gone, people attribute that to tigers most of the time. I know leopard detectability was similar regardless of detection or non-detection of tigers. So whether leopards were detected was independent of whether tigers were detected or not, because as we saw here, because livestock was negatively associated with detectability of tigers. So it was detectability of leopard was independent of tigers. I have 2 minutes, I know that. Thank you. So now, importantly, the model average detection probability of tiger was higher in co-occupied sites than at sites where leopard was not present. And this is a very interesting result of why we see that. So that could be because in co-occupied sites, that means we are talking about the sites where there are leopards and tigers, where wild prey is less in number. So tigers must venture outside a lot, and maybe they get detected a lot. But when leopard was not present, that means there could be potentially the sites where core areas of tigers where there are tons of prey, as I mentioned earlier. That's a prey-rich area, so they don't have to wander around a lot to find prey. So this is another interesting result here. So the occupancy of leopards when tigers were not present was way higher than when tigers were present. That kind of tells you, in this model context, that tells you that leopards occupy areas where there are no tigers. That means some sort of habitat segregation is going on. And again, to remember, based on different covariates that we have included here. So what we found basically finally was our model average species interaction factor was way less. It was less than 0.662, which clearly concludes that they do not co-occur in fine scale site. Okay? But if you think about from a habitat whole predictor area, then these leopards are relegated towards the sites, towards the periphery of the park, where there is more livestock, easy prey for leopards, and there are more human disturbance, which leopards can withstand compared to tigers. So co-occurrence is possible in the whole predictor area when you talk about the whole area. But if you think from a fine scale perspective, then they strongly avoid each other. So with this, I have some conclusion I want to go over more time. So if you have any questions, so the final conclusion is that there is strong avoidance between tigers and leopards at fine scale investigation as a result of human and livestock disturbance. So with this, if you have any questions and if I have time, thank you.